All right, so how you guys doing today? I'm good. Yeah, at least it's Friday, right? So we'll have a weekend. Just good. All right, so the last time, let me remind you of what we did. So the last part, we wanted to make the halohydrine formations. Okay. So the one we tried was this one. Then we tried it with the halogens. Okay. So we, like I said, maybe not so much fluorine or the iodine, but the two best halogen we could try on this halogenation would be the bromine or the chlorine. Okay. So anyway, and then if you can do it with the water. Okay. So what happens is the when it gets down to okay, so they can actually go to this one. Okay, so they will have sort of this form, bromonium ion. Guys, remember this, right? And then this is why when they go, okay, the water comes in, and then later the hydrogen, so water comes in, this one, right? Okay, so this one becomes, so eventually you're going to have this one, this one. So this is what we did before. So this is a bit tricky, like I said, that's why I stopped on the Wednesday. So the point is though, because of this, in the process, we're gonna have a bromonium ion that makes those addition on your halogen groups and also your water groups, or eventually hydrogen groups in here on the opposite side. And also, this is in transport position, that's why they are, and also transport position as well, okay? So this is a bit tricky. So maybe can you guys try this one then? Maybe it's a cis. Okay. Try to do it with the same thing. Okay. Go ahead. So once again, the halogen groups, the water will come onto the opposite side because of the, you'll see that the bromonium ion formation in the middle of the process. So not on the same side, but yes. And then this is in cis. Okay. So the one thing you can do is what? Think about the implied hydrogen as well. Okay, about 1 or 2 minutes, we'll do this together. Okay, implied hydrogen there. I was just kidding. Okay, about 30 seconds, we'll do this together. Okay, so let me do this one. Do you hear that too? Okay. So it's the same thing here, but they will be in the top and bottom, and this is this position, so on the same side. the other two. Make sense, right? You wanna do one more? Okay,
Yeah.
let's do one more. So just copy this one. You can do, how about this one? Maybe you can do this one. Okay, another 1 or 2 minutes, we'll do this together. Make sure you put the hydrogen group on the opposite side. So you don't have to know the mechanism, it's okay. Just remember they're coming onto the opposite side, and this is a trans. Okay, so try to put it as a, and think about there's a implied hydrogen as well. Okay? So try to use this. Okay, 30 seconds. Okay, so you can do this one, right? Okay, so on the opposite side, and this is the transform. So this one. Okay, so we kind of care about this one because this will tell you about stereochemistry involved type of problem. So even though it's now a single bond, they'll have a stereochemistry. So can I move on? Can I move on? Okay. So so only thing you really have to think about for your product, they're coming on the opposite side, halogen and hydroxy group eventually, and those are the transients will. Okay. So if that is that's for the hydrogen information here. The next one is the hydration. So if you have this one, you can treat it with some aqueous solution with water, obviously, and some acidic conditions. Okay. So if that happens, you have a hydronium cation. Looks like this. And then, as you know, the tab electron in the p orbital and the pi reason, that we're actually going to attack something that is positive. So they can. So if that happens, okay. But this is now getting this one, right? So this will get to. So no double bond anymore. There's a hydrogen now added on here, okay? And then that makes this position what? Positive charge, which we call carbocation. Remember this, right? And then you can have water comes in. And as you know, if you look at the oxygen here in water, it has a 2 lone pair. So it's good to attack the positive charge carbon here, carbocation. And then this will be on to here. Okay, this is 1, 2, 3, 4, 5. this positive charge, which, as you know, is very unstable, right? So there's another water. We'll take this one. It goes there. So then this will be that these two have electron are now on this. So there'll be positive charge will become, and this will become this. So eventually you're gonna have this. So you have water, the hydrogen, well, the hydroxy groups and hydrogen attached together is like water. So we call this a hydration. It's like water. Okay, makes sense, right?
You see another one?
Yeah. Also, of course. So this is the what? Okay, that's one. So let's do one more. Actually, I'll show you the other one because there are some things I want you to know. Okay. So if you have this one, okay, this one, then same thing happens whenever you have a hydrogen cation. They try to catch the hydrogen cation. Okay. Okay. So then they try to catch this one, and then here, same problem where we already did in chapter 7. Okay. So in this case, you have two carbons. We can put the hydrogen on it. But when they do this, they're gonna do it in this way, not here. Can you guys guess why? So, see this one here? It's double one here, right? And they're gonna take this one, okay, to grab it. But either you can put this on this carbon or this carbon, but they do this one, not here. Can you guys guess why, based on what we learned before? So if you put the hydrogen over here, this is where you're gonna have what? Carbocation. If you have a hydrogen here, this is where you're gonna have a carbocation. So let me show you. Which one is more stable? Perfect. Because it's more substitute. Okay, so hyperconjunction and what? Conjugation, hyperconjugation and induction that makes more stable carbocation. So the hydrogen will be attached to here. And then water will come into this side. Does it make sense? Because this is what we learned before. So then this become this one, right? And then another water will grab this one, this. So this positive charge will be gone, and these two will make this. Okay? So eventually you're gonna have what? Well, you can say hydrogen, but you don't normally show the hydrogen, right? So it's a hydration. Okay. All right. Does it make sense? Can you guys do this one? The only thing that you need to know from this part is you're going to put the OH hydroxy group on the more substitute carbon, that's it, and remove the double bond. That's all you need to know actually, because you don't have to know the mechanism. It only helps you how it happened, but for your exam, you only need to know. So if that happens, you just need to do here. Okay, you have this one over here. So you have hydration like this. I'll remove this one here, right? And then this is more substitute than this one, right? So just add. That's it. You have a hydrogen here, but you don't have to show it's implied hydrogen. So the answer is just it's pretty easy, right? Actually, you only need to know how it happens, and you know the trick now. Okay. So just one more thing. All right, let's do this one then. Okay, let's try to this one. Okay, and then we'll move on. So let's do this one. So do you know the trick now? It's much easier. So if there is two carbons in a double bond with the hydration, try to find which carbon has more substitute, potentially better position for carbocation, and you can try to put the hydroxy group, OH groups there. That's pretty much it. Okay? Then you got the right answer. All right, so what's the answer? So I'll show you the answer here. So I'll just find this two. I'm gonna remove this one. There you go. You got the same answer, right? Perfect. So I'll move on. Makes sense, right? All right, so the next part is the kind of the same, but we call this oxy mercuration and demercuration, same, but you just can say oxymercuration. So this one is something what we're gonna do with the. This is a bit tricky. So once again, you don't have to know the mechanism, but I'll just do it for you. Okay, don't worry about it. Okay. So we're gonna use in here. We're gonna use mercury 2 SK, okay, mercury 2 SK, and with water, okay, with water, and then we actually going to do it in some organic solvent, okay, here, okay, and then later we're gonna treat it with the sodium borohydride, Okay, so I'm going to explain why is it happening this way. Okay, so this mercury 2 acetate is looks like this. Okay, it looks like this. So you have a 2 acetate, or kind of bond to the central mercury here. And then what happens to this one is they try to steal one of the pair of electron and the previous in the double bond. So one of them break up like this because they got the electron here. Okay. So this will become positive, right? Because it's now lost electron. So then they're coming in. So this one will there. Okay. So what happens to this one? There's no more double bond, right? Because now they use the pair of electron to touch this one. Now it's also taking this carbon here. So they make this. So I'm just gonna put now only one acetate because it lost one. Okay. So there was 2. Now it's only 1. Okay. Makes sense, right? And then what it does is if you look at this one here, this is also the same what we're gonna do here. This is obviously unstable, right? So they wanna detach the one of them, either this one or this one. Okay. So either they can attach to, if they break this one will attach to here. If you break this one, they'll attach to here, right? If you break this will attach to here, right? Okay. So, but they will break this one. Can you guys guess why? Same reason. It's more substitute or more stable. Perfect. Okay. Makes sense, right? Okay. And then water comes in. It's actually the same. Okay. And then later, this will also pick up by another water. So, okay, I'll show you step by step. So once the water goes there, right? Water, get this one, so this will goes to here, so plus charge will be gone. This, okay? And then we use the sodium borohydride. So sodium borohydride looks like this. Okay, and then the bond is actually 3, but it has 4 hydrogen here, right? So it'll be negatively charged. So they kind of pair up like this, and then this negatively charged. They're really good at donating the hydride. So not just hydrogen, but hydrogen with a pair of electron. So they can be neutral, negative charge. So they push, so they gone. So it's the hydration too. Make sense, right? So you don't have to know the mechanism. So the trick, I'll tell you the trick here. Okay? So the trick is, so this is just Stolben, okay? Don't worry about this one. But the trick is, you have also same. You have 2 carbons over here, right? And then this part is more substitute, right? And just try to remove the double bond at OH. That's it. There you go. So if I give you this one, can you guys try it? Maybe theoretically at least what happened to you? Oh, sorry, this one. Just 1 or 2 minutes, but it's pretty much the same. To get the much more stable intermediate, we need to have some more substitute carbon. Will have that addition of the hydroxyl group. Okay, so but with a different method here, I guess. Alright. Okay, so yeah, you guys will get this one, right? Okay, you get it, right? So I know there will be hydrogen, but you know, it's hydrogen, you don't have to show it in the, yeah, so you can, right? So I can move on, right? Can I move on? Okay. Alrighty, so, next part is okay. So this is a bit tricky, I guess, but if you have this one here, you can actually treat with the Doré with some organic solvent here, and later you can treat with the hydrogen peroxide and a little bit of basic conditions there. And what happens here, once again, you don't have to know the mechanism, but I'll do it. So you can do this one here. So if you look at this one here, this is how it looks like. Okay. And this is what it looks like, right? So they're actually coming on the same side. Okay. So because this is the same, they're all in the same compound. So they're coming into this position. Okay? They're coming into this position here. They cannot coming into this position. So there's two possible scenarios, right? They can coming into this way or this way. But this is not possible because this is more branched. This is more substitute. So this has a very limited space here. So this is also have some space problem here as well. So they don't want to coming in this side, right? But if they're coming in this way, it's much easier for them because it's less substitute. Make sense, right? So then when it hit that, so with this double bond here and the bond here, right? They make some kind of this weird intermediate like this transition status. So eventually what happened here? This one, okay? Okay, yeah. So here was one. Oh yeah, sorry, I missed this one. Anyway, it doesn't matter. So if we got to here, we're gonna treat it with the hydrogen peroxide here. Okay. So what happens to this one? Obviously, oxygen is what? More high electronegativity, negative. So this will actually goes to there, and hydrogen will lose the electron here. So this will become negative. Okay. So this is not even the textbook, so you don't have to know. But I'll tell you the trick later. Okay. So this comes to have a 3 lone pair now. It's really able to attack something that is something. So they goes to actually here. Okay. So they have this one attached to this one, so this is gone, and this become negative. Okay. And then what happens to this one is now you have this one, right? And they switch this bond, this carbon to this one to this. And then this one goes to here. Okay. So then what happens to this one is they actually break apart. So they leave this one and they leave this one too. And they later grab, so negative charge oxygen will grab one of the protons. Okay? Water or the hydrogen, and then they become hydrogen. Okay? So the obviously you don't have to know everything, but what I want you to remember from here is you have to do exactly the other way. What we did for oxygen maturation. So I'll show you. So this will become. So when we had this one over here, right? Okay, and try to find the 2 carbons in a double bond and just erase it. And then find now at this time with this boron, find the less substitute one, not the more substitute one, and put away. That's it. Okay. So we actually do this in this order because we actually wanted to know is actually happening in the opposite position, the hydrogen. Okay. So yeah. All right. So maybe. So we'll do the same starting method here. Maybe you can try. Okay. So this is what we did with the oxygen maturation. But how about for this one? Okay. Let's try to. Yeah. Okay. All right, so I'll show you the. So this is gone. So I'm gonna add. This one. So you just need to find this one, okay, and then goes to over here, okay. But the thing is those two, because you remember those were coming on the same side, but they should be on the same side too. That's why it's pushed on the other side, these two. So what you you'll see is there's a hydrogen here, and you just need to, these two push on the same side, because the borane came on the same side. Maybe it doesn't matter if you're from the top or the bottom, but they're coming on the same side. Then push this one to the other side. So they maybe push on the forward, they're coming on the back together. That's why they still stay as a back side. Only difference is replaced by one hydrox group on the same side, and these two are still on the same side. Okay, because they pushed on the same, the two groups on the same side, these two groups are pushed on the same side. Okay. Alrighty, let's do one more. You're gonna do one more? Okay, let's do one more. Okay, spot this one. This one. Okay, maybe I can show you. Is it implied there? So. Okay, 1 or 2 minutes, we'll do this together, don't worry about it. But if you know the trick, oh, it's really easy game now. Okay? Okay, so what I'm gonna do is I'm going to eliminate this double bond here, okay? And then these two carbons, this is a less substitute, okay? So I'm gonna add hydrox group, and hydrogen are here, so they push on the same side. That's it. Make sense, right? Okay. Can I move on? Okay. So this all hydration is what we call more like the oxidation. But now we can do some reduction. The best way, one of the best way to do the reduction is what we call hydrogenation. Simply meaning you try to saturate your carbon with the hydrogen. So what you can do is if there is a double bond somewhere, you can treat it with the H2, okay? And then you're going to have some help from some catalyst. This is a palladium with the charcoal, like there. And then what it does is just make the hydrogenation. So just simply putting the hydrogen on where you have a double bond. Okay? So that's the thing we can easily do with the reduction, hydrogenation. Okay? Hydrogens, molecules, and the palladium within charcoal. So this one is something you have to know, but there's several things I want to tell you, so I'll tell you now. If you have this one, okay, here, only thing you have to do with this one is try to remove the double bond, that's it. Okay, but just remember, you cannot reduce the carbonyl group here. Okay, you cannot do you cannot reduce carbonyl group because it's much stronger. Only the one in the regular double bond can be reduced. Okay. All right. So then there's another thing. If you have, I don't know if I'm gonna do this. Here, if this is a phenyl group, this is do you see the double bonds one another with a single bond and double bond, single bond, double bond, single bond, right? This is what we call aromatic ring. We call this very highly conjugated. So it shows the very stable. So highly conjugated means they have a lot of electrons, and the pi electrons are delocalized in the ring structure, which you're gonna learn in Auger 2. Are you guys taking Auger 2? Yeah. So we'll not spend quite a time on it here yet. Because of that, you cannot also reduce in the aromatic ring. This is very stable. So this one either, right? These two cannot. So you only can reduce this part. Actually, you can reduce this one, and this one at a certain position you can reduce it only only special conditions. But just in regular method like this one, it only can reduce the one that is regular double bond. Okay? But you don't have to worry about the one that reducing this one. This one it is also be covered over too, so you don't have to worry about it for now. But for this one, I just want you to remember the one with the carbonyl groups, the one in the aromatic ring, like single double, single double, single double, in the ring. Does it make sense? So let's try the one. Oh, there's yeah. Let's try the. Yeah, I'll just stop here. Okay. So the